Okay, rounding out our last talk of this session, we're going to hear from Manish Marwah. Manish is a research scientist at OpenText, and he's going to be presenting his research, Is F1 score suboptimal for cybersecurity models? Spoiler alert, I bet it is. Introducing Cscore, a cost-aware alternative for model assessment.
So, hi, everybody. My name is Manish Marwah, and I'm very excited to present this work at CAMLIS. So this work doesn't, it's not about, say, LLMs or deep learning. It's actually about something more mundane, but something that's used pretty universally when somebody's building a machine learning model that is using the F1 score. And we ask a very simple question here, is F1 score a good metric to use for cybersecurity applications? This is joint work with Asad, Stephan, Martin, and Marwah. Okay, so machine learning models are obviously widely used in cybersecurity. That's what this conference is all about. So there are applications like the intrusion detection, malware detection, phishing site detection, and so forth. And during the machine learning model building process, models need to be evaluated. And the most common evaluation metric is F1 score. And F1 score works very well. It works well for skewed data as well. But one problem that F1 score has is that it treats false positives and false negatives the same. As an example, if you have a model that detects ransomware, so there, if you get a false positive, an analyst needs to look into it, and that may cost, say, a few $100s of the analyst's time looking into investigating that. But if you have a false negative, you've essentially missed an attack, and that could cost you, say, millions of dollars or more. So clearly, a false negative there is much more expensive or costs a lot more than a false positive. In another example, let's say if you're looking at if the attack is something like a port scanning attack, there it's they're a false positive. Again, would cost you maybe several $100s of an analyst's time, but a false negative may not be that bad, right? So, in fact, in that case, I would argue that a false positive may be more expensive. So in this research, what we try to do is try to come up with an alternative for F1 score that is cognizant of the differing costs of false positives and false negatives. So this is the outline of the talk. I'll start with a brief definition of what F1 score is. Most of you, I'm sure, are already familiar with it. And then I'll talk about some of the related work in cost-sensitive learning. And then talk about Cscore, the cost score, which is a new score that we introduced to replace F1 score. Talk about some of its characteristics, and then talk about experimental results. We experiment with 5 different data sets and compare F1 score with Cscore, and then finally the conclusions. So everybody here is familiar with the errors that a machine learning model can make. And both false positives and false negatives are bad because false positives result in alarm fatigue and can be very expensive. And at the same time, false negatives are very expensive too. The best way to look at model errors is through a confusion matrix. and looking at the various elements of it. Again, this is all kind of, you're all familiar with it. And the typical metrics that are defined are recall and precision. And precision can be kind of thought of as the overhead on an analyst, whereas recall is determining the number of, the fraction of the positives that are detected. There's also false positive rate, but if you have a very skewed data set, it's a little inconvenient to use because your N there, the number of negatives can be very large. So to compare models, you need one number. So typically that's the recall and precision. They're combined together into an F1 score. It's the harmonic mean of precision recall. So F1 score is very advantageous. I mean, in the sense it works well when you have a very imbalanced data set, because you're ignoring kind of the total number of negatives. It is also only high if both recall and precision are high. That's because of the nature of the harmonic mean. But it also have this drawback in our context, which is the fact that it treats false positives and false negatives the same. So looking at the cost of misclassification, that's obviously not something new. People have been doing research in cost-sensitive learning for decades. And there are usually two approaches to cost-sensitive learning. One is to incorporate the cost into the learning method. So where you essentially change the, you're changing, say, your loss function to account for the fact that the cost of the errors are different, right? So you can also do that by changing the ratio of the class ratio in the data that you're using for training. So there are multiple ways of doing that. Another approach is to keep, it's called the wrapper-based approach, where you are retaining, you're not making any change to your learning method, but instead you train a model and then you build a wrapper around it, or use some other method to actually achieve cost sensitivity. And one way of doing it is just model threshold. So the way you pick the threshold of a model, you actually take the cost into consideration. Oops. So in a general sense, what you can do is you can construct a cost function from the elements of the confusion matrix, and then use that cost function to come up with your threshold. People don't normally do that because it's involved, and you need to kind of think about what those costs should be. And F1 score is kind of the easy metric to use. So our solution is to use Cscore, which also, like F1 score, is composed of recall and precision, and another factor here called cost ratio, the RC here, which is the cost of which is the ratio of the cost of a false negative to the cost of a false positive. And this measure can replace F1 score in any of the tasks where you need model evaluation. So for example, for thresholding, for selecting hyperparameters, for feature selection, model selection, and so forth. Now, how did we come up with this, how did we come up with the Cscore? So the next part of the talk of Cscore, where we look at the costs of, compute the costs of false positives and false negatives. So we already looked at the confusion matrix. This is looking at the confusion matrix from a probabilistic perspective. So we have, so this is a binary, this is for a binary classifier. So in our ground truth, we have, so for simplicity, let's just call the positive class as a vulnerability. So that's the V here. and and then you have the not V, which is the negative. And similarly, the classifier produces an alarm, that's the A, or it does not produce an alarm, which is not A. So your true positives can be thought of as a joint probability distribution of these two variables, right? Your false, so this is your false positive here, which is the joint probability of producing an alarm when there is actually no vulnerability. Your false negative is a joint probability when you have a vulnerability, but no alarm is produced, right? And then these numbers along the rows and the columns are the marginal probabilities. The PV is also called the base rate. That is the rate of the positive class in your data set, and typically it's very low. And now we can define the same metrics recall precision in terms of conditional probabilities. So we have the recall, which is the conditional probability of seeing an alarm when you have a vulnerability, and precision, which is again defined, on this row here, which is the probability of an alarm actually being a vulnerability. And you can see actually that recall and precision are kind of, the reversed conditional probabilities, so they're related through Bayes rule, and you can have very high recall, but still your precision could be very low. One reason being, that your base rate may be very low. And that's called the base rate fallacy. Considering that, then we can try to estimate the cost of errors. So the number of false positives is essentially just the total number of data points that you have into the probability of false positives. And similarly, you can compute the number of false negatives, and then you can combine them to get the total cost, which is the cost of one false positive into the number of false positives, plus cost of one false negative into the number of false negatives. And then you can substitute from the above equation. And then finally, you can, so essentially, you can factor out some of these quantities, like the total number of points, and you can and the cost of a false positive, and by introducing this ratio here, the cost ratio, which is which we looked at earlier also, which is the ratio between the cost of false negative and cost of false positive. And so finally, you get this cost here at the bottom, and essentially it is the sum. Essentially, it is the sum of the probability of false positive plus the cost ratio times the probability of a false negative. So now our goal is to try to see if we can redefine these probabilities in terms of precision and recall. And I will not go through all the details. There are more details in the paper, so I would go through this quickly. So yeah, so this is the same expression as in the previous slide. So the cost is proportional to this expression here, the sum of these two terms. So here we try to rewrite the cost of false positive in terms of precision and recall. And this is what we get finally. Again, I'll skip over the details. So you get this expression here in terms of precision. R is the recall and the base rate. And similarly, you can try to rewrite the probability of false negative also in terms of recall and the base rate. And then we combine these two together. So this is what we got in the previous two slides. And we put it back in the original equation there to get this expression for the cost score. So and again, so the good thing here is that the base rate also actually factors out, and that is something that will be constant for a particular data set. So that also we can factor out, and this is the final expression that we get for the cost rate for the cost score. So looking at some of the characteristics of cost score, so this is F1 score. This is a precision recall graph, and the dotted line is actually the precision recall curve for a model. And the blue lines are ISO curves along which F1 score is constant, okay? So we can try to draw similar things for C-score, and that's what it looks like. So the top part is more relevant, and you can see the curves kind of look very similar. So this is for a cost ratio of 1. So we're giving equal importance to false positives and false negatives. Here we are changing the cost ratio. So the cost ratio of 10 is the the cost ratio is the ratio of cost of false negatives to false positives. So cost ratio being 10 means we are giving more importance to false negatives. So if you see here, and false positives false positives relate to precision. The higher the precision, the lower the number of false positives. And false negatives relate to the recall. That is, higher the recall, the less false negatives you'd have. So you can see here in this plot here, if you change so if you move along the recall direction, the cost changes much more than if you move along the precision direction. There, the cost doesn't change much. This is the reverse case where the cost ratio is 0.1. So there you are, there you are giving much more importance to the false positives, and you can see that in fact that's the part to kind of pay attention to up here. You can see here when you are changing the along the x-axis, that is along the direction of the recall, there isn't much change, but if you change precision, then the cost changes more. One natural question is that when the cost ratio is 1, that is when you give equal importance to false positives and false negatives, is C-score the same as F1 score? So to be able to compare, this is what the F1 score is. To be able to compare it with C-score, we have to actually convert it into a cost, because F1 is not really a cost, right? It is bound between 0 and 1, and the higher it is, the better it is. So one way to convert F1 score into a cost is to transform it like that, like 1 over F1 minus 1. So now when F1 is equal to 0, the cost goes to infinity, and when it's 1, then the cost is 0. So we tried to compare the F1 cost with the cost score, and when cost ratio is 1, it turns out, again, I'm skipping over some of the details. It turns out the cost score is proportional to the total sum of the misclassifications, and F1 cost is also proportional to the sum of the misclassifications, but it is also inversely proportional to the number of true positives. So they're not exactly the same, but they're very similar. And in practice, we found that they do look quite similar. Okay, so I'll quickly go over the results. We experimented with 5 different data sets. And for each of the data set, so these are all binary, we trained binary classifiers on them. So And the goal here is not to train the best model, but it's just to get a reasonable model so that we could compare F1 score with Cscore. So this is the first data set. This is actually an intrusion detection data set. And this is F1 score. And the x-axis is the output of the model. And based on F1 score, this is the threshold that you would pick. The numbers there in the brackets there are precision and recall. Now, if we used Cscore, for the same model, in fact, at cost ratio 1, which is the middle figure here, we actually get the same threshold. But when we use a cost ratio of 0.1, the threshold increases as you would expect because you give false positives more importance. And then if you use a cost ratio of 10, it decreases. This is another example. This is credit card fraud data. So here, there is a difference between the thresholds picked when the cost ratio, using cost ratio and F1 score. But here, actually, what you see is that one thing to note is that the F1 score is pretty flat over the different values, right? So there isn't actually that much difference between these 2 points. But in Cscore, you are optimizing the cost. So you're basically, again, for the different ratios, you're actually getting the threshold which optimizes the cost. I will skip over the next few results, which are all very similar. Another way to kind of look at it is look at the precision recall curve for these points and see where the F1 score is optimized and where different cost ratios are optimized. Now, obviously, somebody can just look at the PR curve and just decide from there what is the best point to operate at. But having using something like a cost score lets you it makes it more systematic and lets you pick a point which is kind of optimized for your costs. So so this is a summary plot which shows the benefits of using Cscore compared to F1 score. So the point in the center there, the 0 point, that corresponds to a cost ratio of 1. And as you go away from it, you see that the percentage difference of using F1 score as compared to Cscore, the savings increase. So in conclusions, F1 score is very useful and it's used quite uniformly, across different problems. But it has the drawback that it treats false positives and false negatives the same. We propose an alternative to F1 score called Cscore, and it performs. And we ran several. We ran experiments on several data sets and found that it performs significantly better. And one goal of this work is also to kind of raise awareness amongst machine learning practitioners working on cybersecurity data sets of use of cost-aware metrics like Cscore as opposed to using cost-oblivious metrics like F1 score.
All right, thanks, Manish. That was an incredibly clear and interesting talk. Definitely an important point that many of us gloss over in our eval metrics. So we have a couple minutes for a couple of questions. I think there's one back here.
Yeah, hi, thanks for this. This is actually really important. I'm thinking about it a lot these days myself. How does the Cscore's behavior compare to like F beta, where you set, beta to 0.5 or up to 2?
Right. So yeah, so you can use F beta. Basically, you have to come up with a weight for how you're weighing, precision versus recall. It's possible you might be able to come up, but it's not clear what that beta should be. I think that's the, right, how do you come up with a good value for beta? So, so I think you would need to come up with, some sort of a cost ratio there, and maybe derive beta based on that. So this is similar, but here you have, we explicitly look at the cost rather than trying to guess what beta should be.
Yeah, thank you for the talk. I have one question in regard to the lower bound for the C-score. Like, suppose you have the precision which is quite low, close to 0. How do you handle that compared to F1 score, which kind of uniformly handle the weight between recall and precision? In your equation, it seems like you might have large number when it's close to 0. Like, how do you handle that?
Right. So if your precision is close to 0, clearly your cost is going to be very high. So, I mean, a precision of 0, obviously your model is not very useful if you have a precision of 0, right? So clearly it is not defined for precision of actually, if you get a precision of 0. So we haven't really looked into that, but hopefully, you have models which are, don't have a precision of 0.
All right, one last question. I'm curious okay, maybe 2 questions. In terms of like actually putting this into practice, do you have any examples of where you were actually able to like do this for something in deployment and it made a difference about the threshold you chose? And then second question, also from a practical standpoint, in terms of coming up with the RC ratio to begin with, how difficult do you expect that to be in practice?
Right. Yeah. So that's a good question. So I'll answer your second question first about the cost ratio. How do you come up with a cost ratio? So clearly you have, so when you're developing a model, you have to think about what the cost ratio should be. So I think that's a good thing because, people just assume it should be the same, and especially in cybersecurity, it's very different. So it forces you to think about that. Now, obviously, you may not be able to come up with the right cost ratio, so you can do things like, do it for multiple cost ratios and see what the sensitivity of your model is, of the threshold is, for example, to multiple, sensitivity of the threshold is to the cost ratio, and, kind of do it for that. Your first question regarding, so yeah, we did do it for an internal data set also, and actually I do have results for that as well. So one of the results I skipped over. So yeah, we did get some benefits from using it. It kind of removes the, the guessing work from, picking the precision recall trade-off.
Excellent. Okay, thank you so much. That's the end of this session. So I think we're going to take a break.